Okay, we're going to take our idea of torque to the next level of formality. Now, really, this video is not terribly useful in terms of just the gut application of torque, but it becomes very useful if you want to build on it and apply it to very complex systems. Let's say a solar system or a galaxy or some complex rotational system situation. Okay, so we have said that torque equals I alpha. Okay. And those are vectors, so direction matters. And we've also said that torque is equal to RF sine of theta to get how big it is. Okay, but what about this direction? That's how big it is, but what's the direction? Now, the direction is kind of, well, it's positive if it rotates counterclockwise according to our convention, or negative. If I have an object, this would be positive torque, this would be negative torque. But where's the x, y, or z direction? This is a vector. Vectors need to have a direction I could write down. And because this is all rotation, and rotation counterclockwise is considered a positive, rotation counterclockwise is negative, this is one-dimensional. It's either this way or this way. But when I say it's this way, well, sometimes it's pointing that direction, sometimes that direction. So x, y, or z doesn't seem to make sense here. But there is an axis, a one-dimensional axis, that does make sense for rotation. And that is the axis of rotation. Okay, so the axle, if I drew an axle here going through this would spin this way. Well, as it's spinning around, it's always spinning in a plane perpendicular to that axle that's coming in and out of the plane. So if I were to draw this from a side view, or a 3/4 view, here's a disc, and there's this axis of rotation that's coming out of it. And so if this was positive torque, it'd be spinning around like that. Okay, it's spinning around, coming out at you here, going in away from you there. And so how can we describe what's positive or negative in terms of a direction? And this is called the right-hand rule. Okay? This is a really powerful rule, and it comes into play in torque, and then we'll see it later on in magnetics. It's a very important mathematical principle to help imply directions for things that, rotation or magnetics both apply it. Things that have a perpendicular nature to them. And this rotation has a perpendicular nature to it. Okay, so with that in mind, if I want to figure out the direction of this torque in terms of a vector, well, if this is rotating this way, so this is a top-down view, this is a side view, this is rotating this way, then what I do is I draw an r vector to some point. So that's my r vector. And if my torque is positive, it would be turning it that way. Okay. Now we'll just assume a 90 degree for this case, just to keep it simple. So a 90 degree. And the way the right hand rule works is, first of all, it's the right hand. And I've made so many mistakes using my left hand over my years of physics. So careful to always use your right hand. But basically, it's a convention. We use our right hand and put our three fingers, a thumb and these two fingers, at right angles to each other. So right now my thumb is pointing straight up at you. My finger is pointing up into the right, and my other finger is pointing up into the left. Okay, so I can go like this, and I can get you can see all those three pointing 90 degrees to each other. All right. Now the way it works in the text, it doesn't really matter which one you call first, which one you call R. You can call this R, you can call this R, you can call this R. The text likes to call this one R, this one F, and then this is the direction of the torque. And that's the rule that follows. Okay, but I have found it so much easier to call this one R, this one F, and this one the torque. Okay. Now what is important is the direction you go. R always comes first, F is second, and the torque is third. But what matters is you go this way. Thumb to this finger to this finger, this finger to this finger to this finger, or this finger to this finger to this finger. Okay, it just matters that you go this direction. So I'm going to always use it. I think it's much easier to use it this way. Okay, so if this is r, this is f, then this is the direction of the torque. So in this case right here, I have r is pointing that way, f is pointing up, and my thumb is constrained to point up out at you. Okay, by doing that carefully, r is pointing to the right, f is pointing up the page. That means my thumb is constrained to point out of the page. And so that gives me a direction of the force in this picture, the torque. The torque, the direction is out, or we might put it like this. That is the symbol for out. It's like the tip of an arrow coming out at you. Okay. If it were in, just so you don't recognize the symbols, that is a symbol for in. It's the tail feathers of an arrow going away from you. So you see the tail feathers as the arrow goes away from you, which would be into the page. This would be the tip of an arrow coming out at you. Okay? So that's how we symbolize that. Now in this picture, my R was like this. My F is into. So F is into. Okay? So I'm going to erase that. F's into. R is this way. And so if I go R is that way, F is into the page, which means my thumb goes up the page. Okay? So the torque is that way. Okay? Now, even if they're not at 90 degrees, if my force was something like this, okay, I can still do it. So now R is still pointing this way. F is pointing that way. Now that's the beauty of these fingers is I can do that. Okay? I can do that. So R is pointing to the left. F is pointing that way. My thumb is still constrained to point out, which makes sense. If that was my force, it would have a component this way, which would still cause it to rotate this way, which we call as a positive direction. And so my torque would still be out in that case. Okay? So it doesn't matter even if it's not 90 degrees, the right hand rule still works. Okay? Now generally, there's a mathematical way of representing this perpendicular effect, and we call it the cross product, the vector cross product. We write it like this: R cross F. So that's not a multiplication sign. That is a specific vector product. Okay? And we've already seen one vector product called the dot product, where we got work equals F dot ds. The dot product cares about how parallel things are. The cross product cares about how perpendicular they are. That's why over here I simply said, well, this is just RF perp, or sometimes it's easier to say R perp F. You just care about how perpendicular they are. Okay? And so this is the full mathematical way of doing it. Now, this is specifically looking at torques. We could look at just a generic math, and we can say A cross B equals C. If those are vectors, then to find the direction of C, I would do A cross B. So, just generically, this is the first thing in the cross product, this is the second thing in the cross product, and this is the result. So in terms of our specific application, this would be A, this would be B, and this would be C. Okay? And so that's how we find direction. Now, generally, you're going to just use this. You're going to say, how big is it? Okay, by considering how perpendicular these are. How big is R, how big is F, and what's the sine of the angle between them? Or what's the perpendicular part of F relative to R, or what's the perpendicular part of R relative to F? That's how big you'll find it. And then you'll think direction is, okay, it's going to make it rotate this way or this way. But to be formal, it is a vector, which means it has to have a direction. So if this was the case, and we had X, Y, and Z, then tau would be equal to RF sine of theta Z hat. So now I have been able to fully describe this vector.